one of the cool things that you can do with inheritance is sharing that code like we saw. Like employee's code gets shared into lawyer. The other cool thing you can do with inheritance is this other nice big word for the day of polymorphism. So polymorphism is when you can have one piece of code that interacts with many different kinds of objects, and you'll get different results depending on what kind of object you're interacting with. And so to illustrate this, I have cartoon animals on the screen. The analogy would be like, maybe there's different kind of animals I can talk to, and I tell them to speak, and the kind of reaction that I get, the kind of speech I hear differs depending what type of object I'm talking to. That's a silly example, but maybe I have a shape hierarchy, and shapes know how to draw themselves or whatever. And so if I'm talking to shapes and I say draw, depending what kind of shape I'm talking to, I get a different outcome. Maybe that doesn't make a lot of sense, or maybe it's too vague to make sense. But let me try to show you some examples of this idea in code, and maybe why this is a useful thing to think about sometimes. You can have pointers that don't point to the type that you declared them as. So normally if you make a list node pointer, it points to a list node. If you make an int pointer, it points to an int. If you make a foo pointer, it points to a foo object or foo value, right? But if you have inheritance, the pointer's type could be the superclass, and then the actual object that it's pointing at can be the subclass. That's kind of weird, right? So if you had an employee pointer, it could point to a lawyer if you wanted it to. If you had a secretary pointer, and maybe you had some class called secretary, and then there was a subclass of that called a legal secretary, maybe it's allowed for that pointer to point to that. I can, in my Trailblazer code, I can make a world pointer that points to a map world or a terrain world or whatever. OK, why would I want to do that? Well, the reason I might want to do that is because later on, that same pointer, I could make it point at something else that was some other subcategory. Like the employee pointer Edna, for a while, could point to a lawyer. And then later in the code, I could make it point to a programmer or a secretary or whatever these other types are that are from the same hierarchy. And it's kind of nice to have a variable that can be general like that sometimes. Another analogy would be like if I made a vector and I wanted to store all the people in the company in a vector. Well, what type is the vector? Is it a vector of lawyers? Is it a vector of, do you see what I would have to do? I would have to make one vector for the lawyers and one vector for the secretaries and one vector for the programmers. That's dumb. Why don't I make a vector of employee pointers and store everybody in it? And it'll be OK. It'll work. One of the things that's really important here is if I call methods on these pointers, like if I say, Edna, give me your salary, or what's your vacation days, or whatever, the actual behavior that I will see is the behavior from the object, the lawyer object, not from the employee class. And so you might say, well, why is that? Or should it be that way or whatever? Because it's an employee variable, so maybe I get the employee behavior. But it points at a lawyer object, so maybe I get the lawyer behavior. Like I'm saying, it gives you the lawyer behavior. I think this is the right thing. Because if I had a big vector of all the employees and I looped over them all and I said, what's your salary, what's your salary, what's your salary? I want the specific salary for each of those people. I don't want the generic employee salary. You know what I mean? So if some of them are lawyers, I want the lawyer salary for those people. The reason the code works that way, the reason I get the object's behavior instead of the variable type's behavior is because of virtual functions. It notices that they're virtual, and so it says, oh, I know this pointer is an employee pointer, but the function you're trying to call is a virtual function, so it might have been overridden, so I better check to see, oh, it should use the lawyer version here. So that's kind of how it runs when it works. So here's a couple of examples. If I make an employee Edna that stores a new lawyer, Edna went to Harvard for 5 years. If I call vacation days, it works. If I say I want to sue somebody like Stuart, then actually that line of code doesn't compile. And this is surprising, I think, for people. I mean, I was just saying a second ago that you could do this and that this would work in general. But that particular line, the one that's in red where I'm trying to sue Stuart, that one does not compile. Do you know why that would happen? Or, I mean, we know that Edna is a lawyer. You can see it in the code right there. Why do you think it won't let me sue somebody? What do you think? Yeah.
Employers.
I mean, yeah, basically it's because the employee type doesn't have a sue method. OK, but what about the fact that I know that Edna is a lawyer, and I know that that lawyer knows how to sue people? So in my sense of the world, like Edna knows how to sue people. Why doesn't the code let me, I mean, I know because you said the right answer, which is because the employee type doesn't have that method. But why doesn't C++ understand that? why do you think C++ is getting so confused? And is it good that C++ is getting confused? I mean, is this a dumb thing about the language? Like, what do you think? Yeah.
Like the pointer you've given it is an employee. You've given an employee star pointer, so you just haven't given it the information that it is a lawyer, so it doesn't know that.
Right. She said I didn't give enough information to, I guess, to the compiler. So the compiler only knows that Edna is some employee. And we know that Edna's a lawyer because we set it to be a lawyer. And you might say, well, any fool can see that, it's going to work, so it should just let me do that. But the compiler doesn't have this sort of long-term memory. It doesn't remember that you set it to a lawyer. It just knows it points to some employee. It says you're trying to sue somebody. Hey, not every employee knows how to sue people. I'm not going to allow you to call that. So if I really wanted to do that, I should just declare Edna as a lawyer pointer, not as an employee pointer. If I'm declaring Edna as an employee pointer, it implies I want to just treat her as a general employee. I only want to call general behaviors on her. I only want to call methods on her that employees all have. Another way, if you want to think of it as an analogy, it's kind of like, maybe I've hired her, I've underemployed Edna. I hired her as a general employee, but secretly she went to law school, but I didn't hire her for that job, so I can't ask her to do that work because she's not getting paid for that, or she's not in that job classification right now or something. Yeah.
It seems like you're kind of casting. So would it be possible to make Edna like a janitor and then declare her a lawyer and see if she's
so wait, so you're asking about the casting. Let's talk about casting now. So this piece of code right here is a typecast. What I'm doing there is, for that line of code only, I'm saying, hey, compiler, trust me. Just trust me on this. Edna is pointing to a lawyer, really. And now tell her to sue Stewart. Now the compiler will say, well, OK, I guess if you insist that Edna's really a lawyer, I will believe you. But that only will let you do it for that one line. And then in a future line, if you say Edna, sue Stewart, it will, again, not compile. So just that one line, it trusts me. And so why does that work? Well, because technically when you cast a pointer, you're temporarily creating a lawyer star pointer. And so that pointer, now it does trust to call a sue method on. Anyway, this is kind of getting around the compiler a little bit by doing that. But it works, and it works fine. It does the right thing. But I just wanted you to see, without the cast, it won't do it. OK, you asked me about what if I try to cast something to the wrong kind, I think is what you're saying. I think that's what I have here. So you shouldn't cast a pointer into something that it is not. So here I have employee Paul equals a new programmer. We didn't write the programmer class, but suppose there's another subclass of employee called programmer, right? So it's a new programmer. And then I say, hey, Paul, write some code. And that doesn't compile because the programmer class presumably has a code method, but it's an employee star, so it can't call this method. If I cast Paul into a programmer pointer, I can say code. What if I cast Paul into a lawyer pointer and I said, lol, sue Marty? Weird shit happens, basically, because C++ says, well, OK, I trust you. I'll send Paul in there to run that lawsuit for you. But when it actually goes to run the code, that class in the memory doesn't actually have that method. And I mean, if you want me to get technical about it, literally what C++ does is it jumps to the place in the memory where the sue method would have been in the lawyer class, and it starts running from there. And whatever's there, it runs that. And in the lawyer class, that would work fine. But in the programmer class, that starts doing crazy things. And so sometimes that makes the program crash. Sometimes that makes the program run an arbitrary other piece of code that you didn't want it to run. Basically, it's bad, and it's unpredictable behavior, and you shouldn't do it. So it does compile, but bad things happen. I want you to think of it as though it crashes, because in most cases, it crashes. So that's what I would say. OK, so that's some of the ins and outs of these polymorphic pointers here. So what I like to do is I like to give you these horrible hierarchies of nonsensical classes, and then I try to ask you to interpret what they will do when you call methods on them. That's the kind of stuff I would maybe ask you. Or on a test, sometimes also what I ask you is I say, here's an existing superclass. Write a short subclass that changes it a little bit or extends it a little bit. Those are the kind of problems. Look at the practice test, and you'll see. Those are the kind of things I would tend to ask you. So let's walk through this for a second. There's a snow class with method 2 and 3. There's a rain class that extends snow with a method 1 and 2. There's a sleet class that extends snow with a method 2 and 3. There's a fog class that extends sleet with a method 1 and 3. So of course, these are all just kind of gibberish classes, but I just want to see if you understand the mechanics of it, right? And then what I do is I say, OK, assuming that all those classes have been written, then what does it do when I call these various methods? How do you understand what all the methods do? In some cases, it's simpler or harder than others. So what I think you should do when you want to solve one of these problems is you start out by looking at the 4 classes. And if you look carefully, like, all of them extend something except for one. Like, rain extends snow, sleet extends snow, fog extends sleet. The snow one doesn't extend anybody, right? You know nothing, class Snow. Obscure Game of Thrones joke? No? Okay, never mind. So one of them is like the daddy of them all, basically. And then you want to look down from there. Who extends directly off of that? And who extends directly off of them? And you should write this little tree or picture or something. You could do whatever you want. I mean, I just want you to get the right answer somehow. But this is what I do. I draw a real quick little picture of what the classes are and whose daddy is who. And I write in the little note of like what methods are in each class. And sometimes next to the methods they have, I say, oh yeah, that one prints Snow 2, that one prints Snow 3. If you have a different way of writing this out that helps for you, go ahead. But this is what I do. Okay? I write all this stuff down. The other thing is like the rain class here, I'll go back to the code in a second, but the rain class has a method 1 in it. It has a method 2 in it. It doesn't have a method 3 in it. But since it extends snow, it sort of inherits one. So sometimes in parentheses I write, hey, it has a method 3 that it inherited. And sometimes I just write on the side, here's what that prints. Okay? And I do that all the way down the tree. I write all that out. So now with that in my hands, the actual like problem or question that Evil Marty asks me is something like this. If I declare that and I call that, what does it do, basically? And that's the kind of stuff you have to do maybe on the final. So how do you get the answer? Well, look, you can practice this and get good at it. There's kind of a method to this madness. Here's a set of steps that you should follow. Step 1. Look at the variable type, the blue, on the left of the equal sign. And then look at your little chart that you made. And then say to yourself, does that variable type have this method? Does the employee class have a Sue method or whatever, right? If the variable type on the left does not have the method that you're trying to call, then it won't compile. So if that's what you find out, then you're done. You can move to the next one or whatever. That's the answer. If it does compile, we keep going. Step 2. Look at the type of the object on the right. That's the type that's actually going to run. So look up the behavior from there and see what that type does when you call this method on that type. And then just write that down. Bless you. That's the answer that you would get. So with that in mind, let's do... I want to try something a little different. We're going to do Socrative here. So, but I thought it might be fun if you could see what I always see. A bunch of blank stares. No. Oh, I'm just kidding. I'm just kidding. Look what I'm going to do. I'm going to make it so you can watch yourselves vote while... Oh, wait. I don't know if I can get away with that. Take a look at the picture here and tell me, what do you think it prints when I call method 2 on var 1? See something real quick. Wait, why are these disappearing? Okay. Oops, sorry. Okay, try again. Okay, most of you have voted. There's a lot of A's and a fair number of C's as well. It's always weird when you can see the votes because then you're like, I'm going to vote for the big bar. I'll vote for the one with the most votes, right? It's like you ever watch the political coverage and like underneath Obama and the other guy, they have the like meters of like who people like or whatever. It's like that. So, okay, so a lot of A's and a lot of C's. So the steps here are, again, we check the left side, see if it has a method 2. Does a snow have a method 2? Yes. And okay, fine. So that means it compiles, right? So when we actually look at the behavior, we look at the right side, sleet. We look at its method 2, which prints sleet 2, snow 2. If I went back to the code earlier, where is it? Sleet prints sleet 2 and then calls snows 2, which prints snow 2. So that's what the code does for the method 2 of a sleet object. So, wait, shouldn't it be sleet 2 slash snow 2? Where's the rest of it? So, the 3% of you who put D or E, wait, why doesn't it, did it get cut off? Ah, look, it's right there. Wait, how come I can't see it? Is it cut? Am I crazy? Wait. Wait, where'd that, what was that? I don't know anymore. Well, if choice C had shown up properly, that would have been the right answer. Since it didn't show up, I guess voting in protest for anything other than A, B, or C would have also been more correct. But anyway, I hope you understand, like, you know, a lot of people voted for A, but I hope you understand A would have been if I used the variables method 2, and you don't. You use the objects method 2. So it's important to understand that. The whole confusion of C being a little off doesn't make A be right, so I hope you understand that. But, okay, fine. Let's try another one. Let me see if I can make it not do that. So let's try again. Oh, wait, now, so I think the choices are all visible, but choice D is compiler error, okay? So we've got a snow variable pointing to a rain object, and we're calling method 1. What does it do? Whoever designed this thing, the contrast on the two colors is pretty crappy, isn't it? It's like dark cyan and dark green. Like, come on, guys. Get some contrast up in here. Oh, well. So a lot of you have voted. Go ahead and take a couple more seconds and vote if you haven't yet. Okay, so let's talk about this one. We have a snow variable that points to a rain object. What's the first thing we do?
Snow has a method 1.
Okay, and what's the result of that?
It doesn't. So compiler crash.
It doesn't, so the code does not compile, right? If it said rain pointer points to a new rain and we called method 1, it would call the rain class as a version of method 1, which would print rain 1, which would be choice B, which a lot of you voted for, but it doesn't even get that far. It doesn't even compile. This is like making an employee variable and asking them to code or sue people or whatever. This is just like that. You understand? Okay, so I want to show you one more thing. But, we have a few more minutes here. So it gets a little bit trickier. There's one more layer to this thing. We talked about casting, right? Casting is you make the compiler trust you just for a moment, right? And that can make certain things that used to not compile, compile, right? That's the difference. So if I say snow points to rain and call method 1, we can still follow a set of steps to solve this. It's just we have to add a step. Here's the process. Step 1, look at the type that you're casting it into. If that type has the method you're trying to call, then it will compile. So that's a start. If that type that we're casting it into still doesn't have that method, which could happen, then it still does not compile. Okay? So that's step 1. If it compiles, let's keep going. Now when it runs, I hope you understand that casting it does not change what it does when it runs. When it runs as the type of the actual object that it is. Casting doesn't change who you are. You put on different clothes or get a different job or whatever. You're still you. You're still the same person. That's kind of how we're doing here. So if you actually are deciding that it's going to run, to decide what it does, you look at the type of actual object that it is on the right side of the equal sign. Okay? So that's it. So here's one more. Let's do another Socratic one here. Oops, multiple choice. There. Make this a little bigger. Okay, go ahead. Snow variable points to a rain I call method 1. Pretty dominant vote for choice B, isn't it? I mean, we look at what we're casting into. Does it have a method 1? Yes, so it compiles. And if it runs, it's going to do what a rain does, which is print rain 1. So, right. So that's a pretty straightforward example of, I hope you can tell, if I had not cast this, I would be asking a snow to call a method 1, right? And the snow does not have a method 1, so that would not have compiled. So the cast made this go from compiler error to rain 1. Question, yeah?
If you cast it as a fog, would it do the rains?
Yeah, that's a great question. What if I cast it into something that it isn't? But the thing I cast it into has a method 1, and the thing that it really is has a method 1. So I'm lying, but I'm telling sort of overlapping compatible lies, kind of, right? That's a really interesting question. It still produces unpredictable behavior because it jumps to places in memory that might not line up perfectly. It jumps to fog method 1's place in memory, which might be different than rain's method 1's place in memory. This is subtlety of implementation, but I would still want you to think of such a thing as being illegal. And I would probably not ask you that on the real test, but the actual behavior is that would sometimes do unpredictable things, right? So that's one. Let's look at another one. We still got a couple minutes. So one more. Here's another one. You can vote on it if you want. I've got a snow variable that stores a fog object. I cast it into a sleet, and I call method 1 on it. Wow, some answers are jumping way out ahead quickly here. Yep. Should we walk through this? I mean, snow stores fog, so the variable is here. The actual object is here. I cast it to something that's in between the two. That's kind of interesting. You can do that. That's fine. And then I say, now call method 1 on it. But to get to method 1, you have to be all the way down here in the tree, right, in fog. Sleet still doesn't have a method 1. And so the cast did not fix the issue of it not trusting you in the compiler. You understand? So this is a compiler error, so D is the right answer here. Casting doesn't always make it compile. Yeah?
But if you wanted to call method 2 or method 3 and you cast in sleep, is that what you were saying before, where like it works unpredictably, or it works predictably because you're casting in the tree?
Unpredictable bad things only happen if you lie. And like lying only happens if you say something that the object isn't. A fog is a sleet, and a sleet is a snow. It's just a specific kind of one. So it's not a lie to cast a fog into a sleet. It's not a lie to cast a fog into a snow. Or like if the variable is a snow and the object is a fog, casting it to a sleet isn't a lie. It's just not the most specific thing that you could have casted it into.